my name's Debbie Huck-Jones, and I'm Product Manager for Analytical Imaging here at Malvern Panalytical. Today, I'd like to give you a quick demonstration of the Morphologi 4 ID. This is our automated static imaging system combined with Raman spectroscopy, which gives us morphologically-directed Raman spectroscopy. And this enables you to get component-specific particle characterization. So you can get the particle size or particle shape information about single components from within a blend. It's morphologically directed because we use the morphological information from the static imaging measurement to direct where we get the chemical information from, which particles we'd like to get a Raman spectrum from. So I'll just open up the system and let you see inside. So here you can see the microscope and the sample preparation area. I'm going to take out the sample dispersion unit to prepare a dry powder sample. Within the sample dispersion unit, we have our sample dispersion cartridge. If I open it up, you can see the holes. The sample gets entrained through these holes, and that's how it's dispersed. And this is done by a blast of positive pressure. Today, I'm going to disperse a sample of a dry powder. I'll use our spoons that enable us to take a precise amount of powder and put it into the dispersion unit. I'll just use a second one to level it off. And in the sample goes. I'll then place that into the system and connect the air supply. At this point, I need to close the door whilst I start the measurement, but I'll open it again later to let you see what's happening. Within the Morphologi software, we run a measurement using standard operating procedures, so I'll run the one that I've set up for today. Now I can put in my sample name and set the measurement off. At the start of the measurement, the system does a number of initialization things that enable us to be sure that the measurements are running well and properly. I'll just open the door now so you can see this a little bit. Placed within the stage are a set of calibration gratings. These are certified and traceable back to MPL and NIST. We use these for two things. First of all, we use it to verify the Z position of the system. And then we use it to check the pixel size. So we can see here on the software that it's checking the Z position. This is also using a crosshair target that's within the top light path. It's now swapped the objectives that we're going to use, and it's checking the size of the pixel so that we're sure that we get accurate size results at the end of our measurement. Next, the system goes to the pinhole that's within the stage, and this allows it to get an XY reference. And this is really important if we're going to do the Raman spectroscopy part of the analysis later on, because we need to make sure we're going back to the correct XY position where our particles are located. The system is now checking that we have indeed put a glass plate into the stage. We don't particularly want to disperse the sample all around the insides of the system. It's now dispersing the sample. So you can see a seal is made between the sample dispersion unit and the stage. They come together and close. And you may have just heard that little puff of air, and that was the sample being dispersed. We control the pressure that we disperse it at, the injection time, and how long we allow the sample to settle. I've just done a few seconds today. The clicking that you can hear is the removal of excess pressure, so we don't end up dispersing the sample all around the lab. The sample dispersion unit is lifted, and we can see that our sample is dispersed nicely onto the plate. The plate is now moved under the objectives, and the system does a couple more checks before it continues. You will note, of course, that I haven't touched anything since I've set it going. So although the system needs to do these checks, it's not your time. You don't have to be stood next to the system whilst it's doing them. If you set up your SOP correctly, once you've pressed go, you can leave the system to run. The system is now doing a surface find, and it's going to do a little routine that compensates for the tilt of the plate. I'm sure many of you have done microscopy before, and you'll be aware that if you focus on your sample here, and then you move to a different position, you need to focus again. Well, we don't want to spend a lot of time checking the focus, so we use a plate tilt correction routine to correct for any tilt in the plate. The way we do this is by using the crosshair target that's in the top light path, and we focus the crosshair onto 4 different positions on the glass surface. It measures the Z position at each of those 4 positions, and therefore it can work out if the plate is on a tilt. And if it is on a tilt during the actual measurement, it will compensate for that tilt by lifting and lowering the stage as it scans in X and Y to make sure the distance between the plate and the objective is always consistent. That means you have a consistent focus and your sample will always stay at the same focus. And as long as you set your focus correctly, then you'll have a consistent measurement. For this measurement, I also set the focus previously as a position relative to the plate, so it will always be in focus. And you can see here my well-dispersed sample being scanned in focus, even though you haven't seen me touch anything else. So the system is scanning the sample of a small scan area, and we can see the results being displayed in real time. I'm just going to shut the system now, as that was necessary to have the Class 1 laser safety for the Raman part of the analysis. Now, any of you who have done microscopy, how many particles do you think you would have measured at this stage? 1, 2, 10, with a size parameter only? Well, we've already done 1,700. For every particle that we've measured, we have detailed size and shape information, and we can see the size distribution being updated in real time here. And we could look at, for example, the shape distribution. This is elongation being updated in real time. If we're particularly interested in a volume result, we can convert to volume. This is important if we're comparing to laser diffraction, for example. I've also set a very basic classification to look at the particles that are bigger than 20 microns in terms of circular equivalent diameter. And this is specific for this particular measurement because those are the particles from which I would like to go and get a Raman spectrum. So once it's finished the morphology part of the analysis, the system will determine the particles it needs to go and get a Raman spectrum from. So essentially, it could be from any of the particles that are larger than 20 microns, so it will get them evenly across the sample available to it. Here today, I'm showing you a dry powder measurement, but we can also measure samples that are suspended. So we have a thin path wet cell or a wider wet cell. We can also measure samples collected on a filter. So for example, if you're looking at foreign particle detection, you can collect the particles on a filter, measure them morphologically, and indeed get a Raman spectrum if that's required. The system has now finished the morphology part of the analysis, and it needs to go back and do a few more reference items to check before it continues with the ID part of the analysis. Some of those are a repeat of what we've done previously. Now, a typical morphology measurement takes somewhere between 10 minutes and maybe half an hour, depends on your sample and how many particles you want to measure. But for the purpose of this demo, I've kept it quite short. And that's why it needs to go and repeat some of these checks, because if it's been a while, it wants to check everything is in order. It also needs to do some additional checks of the laser, for example. So in a minute, we're going to characterize the position of the laser, check the position of the spot, and check the focus of the laser relative to the focus optically, because these are all compensated for during the analysis. So here you might be able to see the laser spot. This is where it's characterizing the laser spot and checking its position. Again, this is very important because we go back to the XY coordinate of the particle that we've selected for identification. And we need to be sure when we get the Raman spectrum from it that we are in that correct position. I shall just leave you for a few minutes whilst it continues its initialization, and I'll come back and tell you more about the analysis once it's started again. So the ID part of the measurement is now in progress. This is the particle that the system is targeting right now, and it's in the process of acquiring the spectrum. We can define how long we acquire that spectrum for. In this case, it's just a couple of seconds, but if it's a weaker scatterer, you might define a much longer acquisition time. Here we can see the spectrum of the particle it just acquired, and now this is the image of the particle it's moved on to next. We did the morphological analysis with the 5x, but we need to do the chemical analysis with the 50x. So what you see is that the system goes back to the particle with the 5x, checks it's the right particle, switches to the 50x, and then acquires the spectrum. Once it's acquired, it displays the spectrum. It's also showing us a very basic chemical classification. In this case, I believe that two of the components are caffeine and aspirin. So I've taken pure caffeine and pure aspirin and generated a reference spectrum for each and put that into my library. So for each spectrum, it just decides if it's closest to either caffeine or aspirin in this case. There may be some other things, and we'll look into that in more detail later. So we'll just acquire a few more spectra, and then we'll have a look at the types of information we get for the results. So the system is about to acquire the spectrum from the 10th particle. So we'll let it do that one, and then I'll stop it to show you the results. Now, of course, as I mentioned earlier, you can leave the system to continue measuring unaided. So if you want to measure 1,000 particles, for example, you just leave it running for a few hours, and if needs be, overnight. In the morning, you come back and get the results that you require. So at this point, I'll just press stop and let the system save the data. I'm going to go and look at the morphology results first so that we can see what we get from that. As you might expect, first and foremost, we get images of every particle that we've measured. As I mentioned before, for every particle that we measured, we get something like 20 different size and shape parameters. So we've got a huge amount of detail about every single particle. Here I'm displaying the particles in terms of size, so largest first, all the way down to smallest. And during that short measurement, I measured over 5,000 particles. If of interest, I can sort by any of the shape parameters. So I can sort by elongation or by circularity. Those are the smaller ones we can see now. So we can zoom in. Or again, we can sort by size. Zoom back out again. Whilst the sample's still on the plate, as I mentioned, we know the XY coordinate of every particle. So I can choose to view an original image. So if I maybe want to take an image of the particle within the dispersion, the system will go back to it, and there I can see the particle. I can change magnification if I want to get even more detail on it. Adjust the focus. We could take a Z-stacked image. We could use different lighting conditions, such as top light. I'm not going to show that now, but they're all options that are available to you within this manual microscope window. From this simple data set alone, we then have all the distributions you might expect. So we can look at the circular equivalent diameter by number. It is a number-based technique, so we measure every particle individually. But if you're comparing to a volume-based ensemble type technique, we can convert the result to volume. Then you can compare it to your other techniques. And of course, we have circularity distribution, elongation distribution, as you might expect. If we go back to the main results here, you might have also spotted our interactive scattergram. And this is really useful if you want to delve deeper into your sample and find out more information. So within this window, you can compare any size and any shape parameter. So in this case, we have circular equivalent diameter and circularity, and the scattergram relates them too. And if I draw a region of interest around anywhere in that scattergram, you can see the particle images update to show me about that sample. So I can very quickly classify my results. And it might be that I want to understand the proportion of different types of particles. So for example, these are the less circular particles. I might create a class here. And then I might look at the more circular particles and create a class here. And this enables me to get much more detail about my system. I've just deleted my size class that I was using for chemistry. If I just save this as a result quickly, I can now look at this sample and see the proportion of those different classes. So I did that very quickly, just proportion of needle-like and less needle-like particles. You can look at that by number basis or again by volume basis. Now let's go back to the chemical result. So here we can see all the particles again. And if I go to my filter page, I can choose to remove all the particles that don't have spectra associated with them at this stage. And here we can see the 11 particles which we collected spectrum from earlier. And if I move to the other part of the software, we can now see the reference library. So this is the reference spectrum for aspirin and the reference spectrum for caffeine. And if I click on the particles, we now have each individual spectrum for the particles as I click them here. We have a stacked view and an overlay view, and we can choose to split the spectra if we want to. So here we have our reference for aspirin, our reference for caffeine, and the particle that we've selected. The system does a correlation calculation, so it compares the particle spectrum with the reference spectra and does a calculation to tell us how close a match they are. So if the correlation is 1, it's a perfect match, and if it's 0, it's no match. So we can see this particular particle has a high correlation to aspirin. So clearly it's aspirin. We can click through and see if there's any others. And this one we can see is caffeine, and another caffeine, and another aspirin. But this one I noticed looked like it was something different. So there's something else in my sample that I wasn't expecting. It might be a contamination, maybe I had a dirty sample spoon, or I hadn't cleaned my sample chamber properly, or maybe there's a real contamination. That might be very important to know about my process. Even from this, I could just create a reference spectrum, add this as a reference spectrum to my library, and I could find out how much of the unknown there was, the size and the shape distribution of the unknown, but maybe I want to know what it is. If I right-click, I can choose to send to Know-It-All. This is Know-It-All software from Bio-Rad, and we have a direct link to that software. So we can see the Know-It-All software is already starting its search. Here we can see the particle spectrum that I imported in black and the closest match that Bio-Rad's managed to find in orange. And this tells us it's lactose. They look like a very good match, so it probably is lactose. So now we know our sample was contaminated with lactose. We can investigate where that came from. That might be something very important for you to understand within your process. What I'm now going to do is I only measured 11 particles here, but earlier I ran the same analysis on the same sample. So here, in this case, I actually measured more like 48,000 particles. So this was something like a 20-minute measurement. And from within that, I measured 836 by Raman spectroscopy. And I classified that sample according to the chemistry. So as well as using the scattergram to look at size versus shape, we can also look at correlation from different components. So here I'm looking at aspirin versus caffeine. So we can see there's a region of high density there. And these are particles which are correlating very strongly to aspirin. And over here are regions correlating very closely to caffeine. And using that information, I can create classifications. So here I've created a classification for aspirin, which is if the correlation is best correlated to aspirin and is relatively high, and similarly for caffeine. If I then go back to that result and now look at my classification chart, I can see the proportion of particles that are chemically the same as aspirin and as caffeine. Here it's by number, or if it's more important, I can look at the result by volume. I can also split out the results for each of those, so I can look at the aspirin-only particles and the caffeine-only particles, and we can compare the different results. For example, by circular equivalent diameter by number, we can see the samples look very, very similar. Indeed, by volume, they look quite similar too. Let's look at shape. We can see they're very similar in terms of circularity. However, if we look at elongation, we can clearly see that the two components within this blend are different, and we can see that aspirin is more elongated or more needle-like than caffeine. So that brings me to the end of the demonstration. Hopefully you can see the wealth of information that morphologically directed Raman spectroscopy can bring to you. We've demonstrated a dry powder. It was a blend. We've characterized it morphologically, and we've collected some Raman spectra from over 800 particles in the previous analysis that I did, and I've shown you how you can separate that data and compare the size and shape of the individual components within that blend. Thank you for watching. If you'd like any more information, please contact us at malvernpanalytical.com.